Now, this is the final part of the material selection lecture, which is about the materials and environment. So the objective are as below, which is the first one is to recognize the need of economic and sustainable use of energy and materials, which is including recycling, and then take account of time and other factors. And then the environmental and social consideration applied in product design and manufacture. And then the third will be the to describe how economic use of earth's resource informs selection of materials and process and finishes and etc. So this is the outline. So materials and the environment for the introduction. All human activities have some impact on the environment in which we live. The environment has some capacity to cope with this impact so that a certain level of impact can be absorbed without lasting damage. But it is clear that the current human activities exceed this threshold, which increasing frequency, diminishing the quality of the world in which we now live and threatening the well-being of the future generations. Part of this impact at least derives from the manufacture, use and disposal of products, and products without exception are made from materials. Material consumption in the United States are now exceeding 10 tons per person per year. The average level of global consumption is about 8 times smaller than this, but it is growing twice as fast. The materials and the energy needed to make and shape them are drawn from natural resources, ore bodies, mineral deposits, and fossil hydrocarbons. So the environment is a system. Human society too is a system. The system coexists and interact weakly in some ways, strongly in others. When two already complex systems interact, the consequences are hard to predict. On the left figure, you can see that the list of materials that have been developed until 2000. Design for the environment generally interpreted as the effort to adjust our present design methods to correct known measurable environmental degradation, changes average product expected life. Design for sustainability, which is to adaptation, which is the adaptation to a lifestyle that meets present needs without compromising the needs of future generations, decades, or centuries. On the left is the annual world production of materials, and the lower left is the resource used to generate energy. From this figure, the usage of natural resource nowadays is alarming rate. Thus, we need an engineering design that is sustainable for the environment. This is the international agreement that is desirable, essential in the view of some to reduce global energy consumption. Producing materials from the ores and feedstock requires energy is embodied energy. The following table lists the energy per kilogram and the annual consumption of four materials of engineering. In consumption of each material could be reduced by 10%, which material offers the greatest global energy saving, and then we is the list. So over here you have the embodied energy, which is 1.2 megajoule per kilogram. Over here you have steel 29 megajoule per kilogram. Aluminum alloy have 200 millijoule per kilogram. It's quite expensive and need to the energy to process aluminum alloy is quite expensive. So annual global consumption, which is over here, polyethylene has the highest consumption compared to other materials. So fossil fuel energy consumed in making 1 kilogram of material is called embodied energy over here. So this is the table that you can use to rank materials according to its energy consumption, which affecting the environment. Here you have the list of material over here. So over here you can put it over here embodied energy megajoule per ton, and then annual global consumption ton per year, and then here is the embodied energy megajoule per year, and then annual global consumption ton per year after 10% reduction, and then embodied energy megajoule per year after that, and then saving the energy, this one minus this one, and then you can break it. So you can have the answer like this. For the ranking, the first one will be steel. Okay, and then the second will be the concrete. and then polyethylene will be the last, and then aluminum will be the third. So over here, the saving over here should be in polyethylene. This is the material cycle life cycle. The nature of the problem is brought to in focus by examining the material life cycle. Ore and feedstock, most of them non-renewable, are processed to give materials. Materials are manufactured into products, and products are used. After that, the products are disposed at the end of the product lives. So, a, a fraction perhaps entering a recycling loop, and then the rest are going to the incinerator or the landfill. So energy and materials are consumed at each point. In this case is called phase. Penalty of CO2 and other emission, heat and gaseous liquid and solid waste. So a regulation requiring a 20% reduction of the average gasoline consumption of passenger car is seen by car makers as a major challenge in this case. As for the sustainability is the ability of the Earth's various natural system and human cultural system and economics to survive and adapt to changing environment conditions indefinitely. So natural capital is which is equivalent to natural resource and natural service. So natural capital is natural resource and natural service that keep us and other form of life alive and support our economies. Natural resources are materials and energy in nature that are essential or useful to humans. There are two classification: renewable and non-renewable. So renewable will be the air, water, soil, plants, and wind, etc. Non-renewable resource will be copper, oil, coal, etc. So natural service function of nature that supports life and human economies. For example, the purification of air and water, which ecosystem provide us with no cost. There are four components of sustainability, which is the first one is the nutrient recycling, which is the cycling of organic matter in the soil. And then you have the natural capital degradation, which is the human activities using renewable resource faster than they can replenish. And then search for scientific solution, which is to reduce the degradation of the natural capital. And then number four will be the trade-off compromise, which is to reach an understanding about resource management. So this is the example for of the degradation of natural capital, which is the air pollution, global warming, soil erosion, ecofire depletion, shrinking forests, decreased wildlife habitats, species extinction, declining ocean, fisheries, water pollution. So this is the figure for the material life cycle that you can use in this case. So when you have the life cycle, you need to have the life cycle assessment, which is acronym as LCA. The goal of LCA is to compare the full range of environmental effects assignable to products and services by quantifying all inputs and outputs of material flows and assessing how these material flows affect the environment. This information is used to improve processes, support policies, and provide a sound basis for informed decision. There are two main types of LCA. The first one is the attributional LCA seeks to establish or attribute the burdens associated with the production and use of a product. And then the second one will be the consequential LCA seeks to identify the environmental consequence of a decision or a proposed change in a system under studies oriented to the future. So the diagram over here, which is the ISO 14040 2006, which is the environmental management, life cycle assessment, and principle and framework. And I quote ISO 14004 for 14,040 2006 describe the principles and the framework for life cycle assessment including definition of the goal and scope of the LCA, the life cycle inventory analysis LCI phase, and the life cycle impact assessment LCIA phase, the life cycle interpretation phase reporting the critical review of LCA, limitation of the LCA, the relationship between the LCA phases and the condition for use of value choice. This ISO covers life cycle assessment studies and life cycle inventory studies. It does not describe the LCA technique in detail, nor does it not specify methodology for the individual phase of LCA. The intended application of LCA and LCI result is considering during the definition of goal and scope, but the application itself outside the scope of this international standard. Streamline LCA to overcome the difficulties. Energy using product EUPs requires that manufacturers of EUPs must demonstrate that they have considered the use of energy in their product as it relates to material manufacturing, packaging, transportation, use, and the end of life. So requirement that a full LCA be conducted on each of one one of a manufacturer's product. Manufacturers have thousands of products. The expense in terms of both money and time will be prohibitive. The complexity of an LCA makes for many purposes unworkable. This perception has stimulated two lines of development. First one is to simplify or streamline methods of assessment that focus on the most significant inputs, neglecting those perceived to be secondary, and software-based tool that ease the task for conducting an LCA. This is the metric method. Streamline LCA attempt to overcome this problem by basing the study on a reduced and simplified inventory resources, accepting a degree of approximation while retaining enough precision to guide decision making. One approach is to simplify while still attempting a quantitative analysis, one using numbers. The matrix of figure 3.6 over here shows the idea. The life phase appears as the column headers, the impact as the row headers. An integer between 0, which is the highest impact, and 4, which is the least impact, is assigned to each matrix elements Mij based on experience, guided checklists, and surveys or protocols. The overall environmentally responsible product rating RERP RERP is the sum of the metric elements. So this is the sum of the metric elements over here. So figure 3.6 is the example of the streamlined LCA matrix. This is the ecological footprint can be seen in this figure. Okay, the carbon footprint is the total greenhouse gas emission expressed as carbon dioxide equivalent. This is contributed by energy consumption which caused by an individual, event, organization, service, or product. Built up land is the usage of land mass by human infrastructure. The forest footprint is the deforestation from timber and paper for timber and paper. Cropland and pasture footprint contributed by the food and fiber consumption. And then the fisheries footprint is the seafood consumption. As in 2014, it is estimated that we consume 1.7 times as fast as Earth can renew it, which is contributing to waste generation. Material and energy consuming system. The obvious way to conserve materials are to make products smaller, or make them last longer, or to recycle them at the end of their lives. Materials and energy form part of our complex highly interactive system as illustrated in this figure 15.2. Figure 15.2 shows the influence on the consumption of materials and energy. The green arrow, which is the positive influence, the red is the negative, and the red and green dash arrow have both positive and negative influence. The lasting design of the past are the evidence of industry's ability to create products that are treasured and conserved. But today's industrial design is frequently used as the potent tool to stimulate consumption by deliberate obsolescence and creating the perception that new is desirable and that even slightly old is unappealing. Here, table 15.1 is the use matrix of product classes. We can see that the high, moderate, and low load factor of product divided by energy consumption. We can see that the primary power consuming over here, primary power consuming is the energy intense product, while the non-power consuming over here should be the material intense product. So the material intense product, which is consume a lot of material but consume very less energy or no energy during usage. The choice of material and process influence all the phases: production through the drainage of resource and the undesired by the byproduct of refinement, manufacture phase through the level of efficiency and the cleanliness of the shaping, joining, and finishing processes, and then the use phase through the ability to conserve energy through lightweight design, higher thermal efficiency, and lower energy consumption. And then the last one will be the disposal phase, which is through the greater ability to allow reuse, disassembly, and recycling. So as you can see in the table 15.1, the primary power consuming will be the family car, train set, and aircraft. Okay, this one high power consuming. The moderate one will be the television and freezer. The low one will be the coffee maker and vacuum cleaner. But in this case, all this category over here is energy intense. Over here should be the non-power consuming. So it use a lot of material to build bridges and roads, and also over here to build furniture and bicycle. So this one is the material intense. Next would be the approximate values for the energy consumed at each phase for a range of products. We have energy intense product and material intense product. Civil aircraft, family car, and refrigerator are the energy intense product which consume a lot of energy during usage compared to material phase, manufacturing phase, and also transportation phase. Multi-story parking, not however, and also private house and carpet are considered material intense product, which are energy are most consumed during the material phase. Significant features with important implication. One phase almost always dominates. If large changes are to be achieved, dominant phase must be the target. A reduction by a factor of 2 or even of 10 in any makes a little significant difference to the total. Precision is not the issue. An error of a factor of 2 change very little. Much information about the eco attributes is imprecise. Here is the eco attributes materials, the material production, energy, and emission. Most of the energy consumed in the four phases is derived from fossil fuels: gas, oil, coal, and coke. Not all electricity is generated from fossil fuels. For example, hydroelectric power, nuclear power, and also wind and wave source. Some of the energy intrinsic is stored in the created material and can be reused in one sense or another at the end of the life. For example, polymers, which is the primary feedstock made from oil, contain energy. And then the natural materials such as wood similarly contain intrinsic or contain energy, and this time derived from solar radiation absorbed during growth. The energy to recycle a material is sometimes much less than that required for its first production because the intrinsic energy is retained. So, for example, typical values lie in the range of 10 to 100 megajoule per kilogram. And then this one is the end of first life from the cycle over here, from the natural resource, product manufacture, product use, and also end of first life, which is going to either going to combustion or landfill or recycle. So this one is to introduce the option landfill combustion or for heat recovery, recycling, engineering, re-engineering, and reuse. From the waste collection, normally most of it will go to the landfill, such as food waste and so on. Some might go to refurbish, such as used furniture, equipment, and so on. Some can be used back immediately, such as glass bottle. The one that goes to combustion can be from the food waste and organic waste which does not produce harmful gas. But some material could not go to the combustion even if some harmful gas might be produced, uh, such as automobile tire which able to generate power and reclaim copper wire after it. Materials such as paper, aluminium, and need secondary sorting according to material family, class, and grade. As you can see, these are the 80s and 90s monitor waste. It is called e-waste because the components of these monitors are made from various materials and cannot be extracted easily, such as gold, epoxy, glass, semiconductor, and many more. So, of course, unethical illegal disposal due to some countries has loose law regarding waste. Some so-called advanced countries send their waste to other countries, especially poor countries. These waste usually the hazardous one and very expensive to process, such as electronic waste, chemical waste, and many more. So after the end of first life, the waste usually goes to the landfill. Much of what we know reject is committed to landfill. And then there is a problem, which is the land available to fill in this way is already almost full in some European countries. So the charging of a landfill tax will be employed currently somewhere near 50 euro per ton. And then you need to seek to divert waste into other channels. And then the other route for the waste is the combustion for heat recovery. So materials contains energy, and then to retrieve it and reduce some of the energy by control and combustion capturing the heat. Rather than throw them away, it will be seem better but cumbersome because the need for the primary sorting to separate combustibles and non-combustible material. For example, you need to separate the rubber and paper or paper waste, for example, and also the organic waste from the metal part and glass part. Then the combustion must be carried out under conditions that do not generate toxic fumes or residues, which is requiring high temperatures, sophisticated control, and a specific requirement. In order for the incinerator to be operated, you need to have a uh, good process procedure, and then you need to have a best equipment so that the toxic fume from the combustion is not going to the atmosphere. But rather than this way, sometimes the heat generated from here used to boil water, and then this produce steam and then supply to the industry. So energy recovery is imperfect, partly because it is incomplete, and also partly because the incoming waste carries a moisture content that has to be boiled off. Another route for the waste will be the recycling. So recycling requires energy, and this energy carries its burden of gases. Recycled energy is generally small compared to the initial production energy, and the making recyclable is possible at all an energy efficient proposition. It may be not cost efficient, but it depends on the degree to which the material has become dispersed. In the house, scraps generated at the point of production or manufacture is localized and is already recycled efficiently near 100% recovery. In widely distributed scrap, material contained in discarded product is much more expensive to collect, separate, and clean. Continuous fiber composite, for instance, cannot be re-separated economically into fibers and polymer in order to recycle them, and can be chopped and used as a filler only. This is the recycle fraction of for comparison. For aluminium, 60% of the aluminium cans come from the recycled can. Paper is 50%, and then 25 to 30%, 35% of steel in cars is recycled steel. So recycling for the resurrecting materials, one of the five end of life options, only one meets the essential criteria that it can return waste material into the supply chains, and also it can do so at the rate that potentially is comparable that way at what is the waste is generated. Means that recycle rate and the waste rate is almost similar. For polymer, the recycling process itself involves a large number of energy consuming steps. So you have to chop the polymer, chop the plastic container, for example, and then remove the all the contamination and also the foreign material, for example, the paper and the adhesive and so on. And after that, you have to go to the furnace to melt the polymer or melt the scrap, and then before changing it back into a polymer pellet. So unavoidable contamination can prevent the use of recycled polymers in the product from which they were derived, restricting them for to more limited use. For this reason, the value of recycled polymers, the price at which they can be sold, is typically about 60% of that virgin material. The consequence of this situation is that the recycling of many commodity polymers is low. So okay, because some might say that the recycled glass is okay because you can recycle glass uh, almost 100% similar as the virgin material. But in case for the polymer, some polymer might be degraded due to chemical, sun, UV, and any kind of contamination. So in this case, mostly the plastic over there, recycled plastic, need to be separated from from the foreign material or from the contamination before it can be used back in the uh, input bag. So that's why the sometimes people would say the polymer recycling is kind of uh, not just time consuming but energy consuming, but also can produce a lot of CO2 emission compared to the virgin material production. So increasing of the recycle fraction is a question identification to the top row over here. Standard recycle marks, which is ineffective because they do not tell the whole story. The lower row shows the emerging identification system. Here, polymer failure and weight fraction are all identified over here. So over here, figure 4.3 is the top recycle marks. Sorry, this one it will be the recycle mark for the most commonly used commodity polymers. Bottom is explicit recycle marks detailing the blending, fillers, and reinforcement. The first is the polypropylene 20% talc powder. The second is the polycarbonate ABS blend with the glass fiber. The coding is explained in the appendix to this chapter. Here is some example for the recycle awareness. So increasing the recycle fraction is a question of identification. So over here you can see over here is this one, the wrap is not yet recycled, and then this one will be widely recycled. The foil is widely recycled. Okay, next is the economics of recycling. Recycling has far reach environmental and social benefits. Municipality collects recyclable waste, selling it through the brokers to the secondary processors, who will reprocess the materials and sell them at a profit to manufacturers. The recycling market is like any other, with price that fluctuates according to the balance of supply and demand. So table 4.1 shows the recycling market for various family of materials. For example, for metals, you have steel and cast iron, aluminium, copper, lead, titanium, and all precious metal, which is developed and used for the recycled materials. And then existing secondary uses but not developed as a market, which is paper, metal, foil packaging. So you can see in the table 4.1. Next is the solid waste recovery for US from 1960 to 2011. Nowadays, more than 30% of the solid waste are recovered. So next part for the end of life of the material or the product, which is the re-engineering, refurbishment, or upgrading the product or of its recovery components. Certain criteria must be met to make it practical, and the design of the product is fixed, or that the technology on which it is based is evolving so slowly that there remains a market for the restored product. For example, housing, office space, road, and rail infrastructure for materials. So another one will be the reuse, redistribution of the product to a consumer sector. that was willingly to accept it in its use state, perhaps to reuse it for its original purpose, for example, second-hand car, clothing, books, and objects acquired from those for whom they had. And then another one become waste. The store sell them to others who perceive them to have value. Another one is to reuse. Reuse is the most benign of the end of life scenario. Some company, especially in the Europe, has a legislation requires the recycling rate more than 80% for vehicle manufacturer. Volvo, for example, since 2008, 80% uh, is recyclable, 95% recoverable. For BMW, at least 95% recycling rate. Next is the eco selection. Selection for eco selection to select materials to minimize impact on the environment. Which phase of the life cycle of the product under consideration makes the largest contribution? In the concept, embodiment, and detail phase, eco audit is needed to be done, and after the production life cycle assessment is done. The eco audit is the assessment of energy or carbon dioxide emission over life from material phase to disposal phase, from here to here. Rational approach to the eco-design of products start with the analysis of the phase of the life to be targeted. The result guide redesign and materials selection to minimize the environmental impact. The disposal phase shown here as the part of the overall strategy which is not included in the current version of the tool. So for example, for materials over here is to minimize mass of part, embodied energy, and carbon dioxide emission. Over here is in the manufacture phase, which is to minimize process energy, process carbon dioxide emission. At transportation phase, which is to minimize mass, and then is the smooth, and then the energy mode of transport. In the use phase, which is to minimize mass, thermal loss, and electrical loss, and then at the disposal phase, which is the non-toxic materials and recyclable materials. This is some example of the usage of natural fiber composite in automobiles. In this case, the Mercedes-Benz over here use uh, non-woven mat to make a door panel. So this one is the acoustic panel. I think the one which is absorb vibration and also sound. So you put it in the door panel, and then uh, you should have a sufficient sound absorption material over here. But of course, you need to consider that the composite material are not easily to be disposed, because the composite usually made from the natural fiber, but the matrix will be the epoxy resin. So epoxy resin is quite hazardous, and then the fiber is not easily to be separated with the epoxy. This is the evolution of TV screen from cathode ray tube, or some people might say brown tube, to liquid crystal. So over here, the current technology will be the OLED, organic LED, and the TV screens can be frameless, and the power consumption is considered very low compared to the original one. So in prior to year 2005, for example, the brown tube or the CRT TV weighs like 50 kilogram for a 25-inch TV. So imagine the difference between the TV back days and nowadays TVs is like have a difference like 5 to 20 kilograms difference. This is the example case study for the drink containers. So drink containers provide an example. They consume the most energy and generate the most emission during material extraction and production. So over here you have glass, polyethylene terephthalate, which is called PET, and then you have aluminium can and steel can. So in order to produce this container it consume a lot of energy. So the focus on the material selection to minimize the energy and consequent gas and particle emission. Their production involves molding and deformation, and then the approximate energy for each are listed. All five materials can be recycled. So which container types carries the lowest overall energy penalty per unit of fluid contained? So over here in the table 15.3, which is the design requirements for the containers, the function will be container for cold drink. The containers must be recyclable. The objective is to minimize embodied energy per unit capacity, and then the free variable is the choice of material. After screening the material which is using its constraint, the method and results. The material of which they are made are listed in table 15.5 over here. A comparison of the energy shows that the energy to shape the container is always less than that to produce the material in the first place. Only in the case of glass is the forming energy is significant. The dominant phase is material production. Compared to this one, to produce soda glass have a lot of, use a lot of energy, 4.9 megajoule per kilogram, compared to other material. But for forming aluminium and carbon steel is quite cheap, okay, which is consuming less than 0.15 megajoule per kilogram. But the embodied energy in this material is quite high, considerably high for aluminium alloy, but plain carbon steel is quite low. So the lowest will be the plain carbon steel. The masses of five competing containers are listed in table 15.4. Summing the two energies for each materials and multiplying by the container mass per liter of the capacity give the ranking shown in the second to the last column of the table 15.4. So you just multiply this one. Steel can carry the lowest energy penalty. Glass and aluminium is the highest. So steel can is very cheap. It's considerable having a low energy. The summary and conclusion for this lecture is shown in this slide. Rational selection of materials to meet environmental objectives starts by identifying the phase of product life that cause the greatest concern, which is the production, manufacture, use, or disposal. If material production is the phase of concern, selection is based on minimizing production energy or the associated emissions such as carbon dioxide production. If it is the use phase concern, selection is based instead on lightweight and excellence as thermal insulator or an as electrical conductor, while meeting the other constraints on the stiffness, strength, cost, and etc. So that's all for now. Thank you very much.